Suta. I am Business Development Manager for GLENAIR, looking after our photonics business. And this afternoon, I'm going to be talking to you about optical components for communications in space. Now, previous presenters have already spoken about the benefits of optical fiber communications, so I'm relieved that I do not have to explain to you all the advantages of using optical fiber. My presentation will mainly consist and focus on optoelectronic components which are used to generate and manipulate light for optical communications. Very quickly, an overview about GLENAIR. We were founded in 1956, and we remain to be an independent and privately owned company. Worldwide, we have approximately 2 million square feet of factory space, and our core products include connectors, connector accessories, wire protection, cable assemblies, release mechanisms such as HDRMs, and also the topic of my discussion today, which is optoelectronics, photonics, and fiber optics. And using these products, we are primarily focusing on military aerospace, avionics, space, oil and gas, and the nuclear industries. Essentially, any industries which requires a ruggedized level of optical communication solution. We have a major focus on new product introduction. Every month we are introducing new products, and we pride ourselves on our service-centric business model. And of course, with a company of our size, we are fully aligned with the quality procedures such as AS 9100 and also ISO 9000 quality standards as well. Worldwide, our headquarters is in Glendale in Los Angeles, and we have further manufacturing facilities in Anaheim in California and also in Chicago. In Europe, we have 3 manufacturing facilities, one in the UK in Mansfield, another one in Bologna in Italy, and our third facility is in Salem in the south of Germany, where we are focusing on HDRMs and electrical harnessing and test harnessing for the satellite and space market. We also have an operational facility, manufacturing facility in South Korea. So this is the agenda of my presentation. I will begin by speaking about optical transceivers and optoelectronic contacts, and then move on to talking about high-density parallel optical communications. And related very closely with that is ribbon fiber optical connectors, which I will also cover. And then I want to spend some time talking specifically about optical solutions for laser communication terminals for inter-satellite optical links. And then finally, I will finish by describing some of our product developments that offer the opportunity to send RF signals on optical fiber. I would like to mention that 90% of the products I will talk about are designed specifically and characterized for space applications. So this slide shows you 3 of our very common packages for optical transceivers. On the left-hand side here, you see a 2-channel optical transceiver. Those 2 channels can be either an optical transmitter and an optical receiver, or they can be both optical transmitters or both optical receivers. In the middle there, you see an optical transceiver with only one optical connection. This is an optical transceiver which uses wavelength division multiplexing to send 2 optical signals on one fiber in opposite directions with full duplex communications. And then on the right-hand side, you see a 4-channel optical transceiver. This can be TX, RX, TX, RX, or it can be all 4 TX or all 4 RX. And with these 3 packages, we can offer solutions starting from 50 megabits per second data rate all the way through to 10 gigabits per second data rate per optical fiber. Now, these data rates can support a variety of different signal protocols, for example, video with HD SDI or 3G SDI or DVI, and also standard data configurations too, like Ethernet, gigabit Ethernet, 10G Ethernet, Fibre channel, RS232, RS422, and also other ARINC data protocols as well. From an optical point of view, these parts are available in all of the common wavelength windows, so 850, 1310, 1550 nanometers, and also on the CWDM wavelength grid. These parts use both multi-mode and single mode optical fiber depending on your transmission requirements and characteristics. Now you may wonder what makes GLENAIR optical transceivers so ruggedized. Well, in this slide here you see at the top a photograph of a commercial SFP optical transceiver. This is a small form factor pluggable optical transceiver. These are used in the quantities of the millions around the world in data centers, in telecom central office type of applications. And as you can see from that top photograph, this transceiver is not very ruggedized. It slides into a Faraday cage. It doesn't have a very strong locking mechanism once it's mounted. And also the optical connector is a plastic LC optical connector, which is a molded optical connector which has no real durability in harsh environment applications. So that was our starting point 10 years ago before we started to develop our ruggedized optical transceivers. So on the bottom left-hand side there, you see a new connector we developed. It's called the GC fiber optic connector, and this connector mates directly to our optical transceivers to provide a very secure optical interconnection. On the right-hand side there, you see underneath, there's a very high-speed electrical connector. That electrical connector plugs into a socket, electrical socket, on the host PCB that our customer is designing. And once it's plugged in, you secure the optical transceiver to the PCB using 4 screws, which screw into threaded inserts on the PCB. It's important to note that once the transceiver is correctly mounted, the electrical connection takes no physical stress at all. All the physical stress, mechanical stress, is borne by the 4 mounting screws that secure the transceiver onto the host PCB. I also want to talk about these optoelectronic contacts. Each one of these devices you see here can be a laser-based transmitter or a photodiode-based receiver. And these contacts are size 8 cavity compatible. And they support, again, a multitude of signal protocols, including fast and gigabit Ethernet, DVI, SIMT video, HDMI, DVI, and also a number of ARINC protocols as well. They run over multi-mode fiber, and they are good for distances of up to 550 meters, and they work off a single 3.3 volt power supply. In terms of the optical contacts, they're compatible with a 1.25 millimeter ARINC 801 or a 2.5 millimeter LEO optical contact solutions. We have radiation test reports available for these products, and those test reports are available on request for customers who want to design these into their satellite communication platforms. These contacts fit into many common connector receptacles that are containing size 8 cavities. So here you see on the top left a regular D38999 Series 3 circular connector. We have an ARINC backplane connector. And on the right-hand side here, we have a new product, which is a D-sub type of connector interface that these optoelectronic contacts are compatible with. Of course, the world is not 100% optical. So on the bottom side there of this picture, you see some examples of custom solutions we've made where we've combined optoelectronic contacts with electrical contacts as well. So you can have a single connector solution which contains an optical signal, power signals, and also some electrical signals, all co-packaged into a single module, into a single connector. So this has been a very successful product line for us. Over the years, we've probably sold more than 100,000 of these contacts into commercial avionic type applications. Now I want to move on to what we call our signature parallel optical communication solutions. These photographs you see here show an optical transceiver which contains a ribbon fiber optical interface. So these are quite compact, but they can transmit into 12 optical fibers in one go through one connector. So these are available in a number of different configurations. We offer these as a 4 by 10 gigabit per second transceiver, or a 4 by 14 gigabit per second transceiver, or even a 4 by 28 gigabit per second transceiver. What do we mean by transceiver? A transceiver is a single module which contains the transmitter channels and the receiver channels in the same unit. So it's a transceiver. We also have individual modules that are standalone transmitters and standalone receivers. And in that case, we offer a 12 by 10 gigabit per second transmitter module, or a 12 by 10 gigabit per second receiver module as well. And in this instance, you're sending 120 gigabits of data along 12 fiber lanes, all in one direction. The optical connector here is an industry standard optical connector. It's called an MTP ribbon fiber connector, and it's manufactured by an American company called US Connect. So in this slide, you also see some environmental information as well. I won't go through it in detail, but I do want to emphasize that everything we make is designed for harsh environment applications. So you can review here the vibration, the shock, the accelerated aging, the temperature aging, temperature cycling, thermal shock, humidity specifications that we test these parts to. And once again, these parts are specifically designed also for space applications. And in my next slide, I will show you 3 different variants of this transceiver. On the left-hand side, you see our terrestrial military-grade transceiver. On the right-hand side, you see our full space-grade transceiver. The key difference between the two is that the full space-grade transceiver uses components that are qualified by radiation lot assurance testing, RLAT testing, and also they're qualified to Group C PCB component testing and screening as well. And they also use a thicker 30 micro-inch gold coating on the input-output connector. So we have different grades of this transceiver depending on what your specific orbit requirements are for deploying these units on a satellite in space. Now, some of our customers had asked us to make transceivers that are even smaller. So we call these the low-profile fiber optic transceivers. These in height are about 7 millimeters off of the printed circuit board. So they are really low profile compared to the previous parallel optical transceivers that I showed you. These again are available in different configurations. So a 4TX, 4RX module which runs over 8 optical fibers, or a 12TX or a 12RX version which both run over 12 optical fibers. And in this case, each optical fiber can support up to 25 gigabits per second in data rate. We offer 2 versions of this. One is connectorized using the MTP ribbon fiber connector, and the other version is a permanently pigtailed version as well. And this just shows you a photograph of that transceiver on a customer evaluation board. I wanted to say that all of the optoelectronic transceivers I described today are available evaluation boards with jumper cables and with test cables. So we make it very easy for our customers to take our transceivers in the lab and get them up and running and testing them running real data using our evaluation boards. Now, with the high channel counts of these optical transceivers, you also need optical connectors. And I wanted to describe here briefly a couple of optical connector solutions that we offer. This is a circular solution. We call it our Super 9 MT. The MT is the black ferrule, which you see in the middle of that connector. And each one of these ferrules can support up to 24 either single mode or multi-mode fibers. And we offer this connector with a maximum capacity to hold 4 of these MT ferrules. So you can see that one connector can mate or demate up to 96 optical fibers. So this really gives you a step up in density in terms of the interconnect capability of this type of solution. We're also making expanded beam versions of this connector, which make these connectors very tolerant to dirt or contamination. Expanded beam solutions remove the necessity to be so concerned about cleanliness of the environment in which they're deployed. The other ribbon fiber connector is what we call our Series 79 MT connector. Whereas the previous one was a circular connector, this connector is a rectangular connector. Here is a photograph of the single MT ferrule version, but this is available in a modular solution to support 2 ferrules and 4 ferrules. So the basic connector supports 24 fibers, whereas the 4 ferrule connector again can support up to 96 optical fibers in a single connector. Again, these are designed for harsh environment applications. These particular connectors you see here are very popular with our avionics customers because they're very small and they can be used in confined spaces where it's difficult to get your fingers to mate a circular connector. Now I want to move on to talking about optical solutions for laser communication terminals. As you're all aware, there is a huge activity in the marketplace right now where operators are launching thousands of satellites into constellations. We have, of course, Elon Musk's Starlink, we have OneWeb and Telesat and many other constellations that are planned to be in low Earth orbit. Now these constellations, these satellites, they need to communicate with each other. They also need to communicate from the satellite down to the ground. And using traditional RF or radio frequency technologies, they are really reaching the limits of their capacity. I think with an RF signal, you may be able to send a few hundred megabits per second of data, but that's about as much as you can achieve. So now, customers want to communicate from satellite to satellite at multi-gigabit data rates. And so laser communication terminals are being developed by vendors out there in the market to address this growing application. This is a block diagram of a typical laser communication terminal. So on the left-hand side, you have an optical transceiver, which feeds a high-speed digital signal into a fiber optic amplifier. The fiber optic amplifier amplifies the signal to 20 watts of power, and the output power from the optical amplifier is fed into optical collimating optics, which collimate the beam and fire the beam to another satellite. So regarding the optical transceiver, the American Space Development Agency is trying to standardize on the wavelengths that lasercom terminal manufacturers can use for these lasercom terminals. They've proposed in their draft standard 1553.33 microns, nanometers, and 1536.61 nanometers. Now, for these very, very precise wavelengths, you need a special transceiver, which GLENAIR has developed, which is our DWDM optical transceiver, specifically targeted for FSO communication terminals. This is a DFB electro-absorptive modulator-based, externally modulated laser 100 gigahertz optical transceiver. And the key differentiating feature of this transceiver compared to other transceivers out there in the market is that it's very, very adjustable using a graphical user interface to optimize the link parameters. And in fact, tests that our customers have done have indicated that it has a 3 dB better operating margin than anything else that they've tested in the market. And again, extensive radiation test reports are available for this part. The other development that we've done for free space optical communications is fiber optic amplifiers. This shows you a picture of a prototype amplifier which is designed to amplify the light signal up to 10 watts of optical power into a single mode optical fiber. Our design is very, very special. It's special because it's very, very efficient in terms of power consumption. So for a 5-watt amplifier, our wall plug efficiency is about 20%. Now that's almost twice as efficient as other competing amplifiers out there on the market. So with that level of efficiency, it makes it a very attractive solution to deploy in satellites in laser communication terminals. We've also just prototyped an amplifier for CubeSat applications. Now this amplifier you see here is much lower optical output power. It's up to around 2 watts of optical output power, but then it's very small. This is only 10 centimeters by 10 centimeters by 4.5 centimeters. So it's ideally sized to fit into a CubeSat type of environment, into a CubeSat form factor. Now, when you have optical amplifiers with such high optical power in the fiber, you also need to have an optical connector that can handle such high optical powers as well. Traditionally, when you're dealing with such high optical powers, people are fusion splicing these amplifiers into their system. And fusion splicing, although it works, has a number of disadvantages because you cannot treat your amplifier like a line replaceable unit. You have to fusion splice it, and it's pretty much permanently there unless you break the splice. So we've developed our I-beam power optical connector, which is a very high power handling connector. With the I-beam power, we have demonstrated 20 watts of optical coupled power via this connector into single mode fiber. That's at 1064 nanometers wavelength. At 1550 nanometers wavelength, we've demonstrated 5 watts of optical power capability, of optical power handling. And this is with a maximum insertion loss of 0.5 dBs across the operating temperature range of -40 to +85 degrees C. So it really is a rugged solution for handling very, very high optical powers that are being generated by these optical amplifiers. And you can see here from these photographs that these high power handling optical contacts we've developed are compatible with standard size 8 cavity pre-existing mil-aero connector solutions, for example D38999 or D-sub connectors or similar connectors. What we found is our customers have been able to test to much higher powers than we have because our power testing capability is limited by the test equipment that we have in our labs. So customers have demonstrated more than 20 watts, which we have not been able to do ourselves. And then finally, I just wanted to spend a couple of minutes on some solutions that we offer for RF over fiber optical links. As you will be aware, sending RF signals on copper waveguide cables any more than just a few distances becomes very, very cumbersome. The optical cables are very thick. They are difficult to bend and route in a confined space. And also, they are not very power efficient either. We've demonstrated that you can send RF signals directly on an optical fiber which has the thickness of a human hair. So we've developed 3 solutions that we are bringing to market right now. The first is a 6.5 gigahertz fiber optic transceiver, which transmits the 6.5 gigahertz RF frequency directly on the optical fiber without down converting it or without digitizing it. The second product we've demonstrated is a 32 gigahertz directly modulated DFB laser solution. So this is really a step up in frequency in terms of the RF signal that an optical fiber can handle using this transmitter. And then finally, we have demonstrated an integrated 32 gigahertz RF over fiber transceiver. This part is a plug-and-play solution. So the customer literally just needs to plug in power, RF signal, the optical cable, and you're up and running without doing any further design work. So these RF over fiber links are now coming to market, and we can provide samples of these to our customers for testing. And so that brings me to the end of my presentation. If you have any questions, I'm quite happy to take them now. We have a booth over in that direction, the GLENAIR booth, where all of the products I've spoken about today are available for you to see and touch and handle, and we'd be more than happy to take you through some of those solutions. Thank you very much.